So folks, we now want to turn our attention to doing calculus, and we want to do calculus on a very specific category of functions called vector-valued functions. What do I mean by a vector-valued function? A vector-valued function is one that takes as an input a real number and outputs a vector. So that's why we call it vector-valued. The output of these functions is a vector. So how could we denote a vector-valued function? Well, we might want to write it this way, where we say r is going to be our function, and it's going to map from the real numbers to Rn. And so here we're going to think of r always as just a real number. There's no reason to kind of imagine it something else. But there's actually a couple of different ways we could interpret Rn. And the first way is it could be a collection of points as our codomain set. So this could be a collection of points. But another way to interpret Rn is as a collection of vectors. And so when we talk about vector-valued functions, we want us to take the perspective that what we're dealing with here is not a collection of points in Rn, but a collection of vectors. So usually what we'll do instead is, rather than just writing a normal letter for a function, we're going to use the bold vector notation to show that the outputs of this function are vectors. So instead what we'll typically do is we'll write r is a vector-valued function mapping from r to Rn. We'll put that bold on it, and I guess when I write it I have to put just an overline bar, but there's a bold typeset of that. So there's a vector-valued function mapping from the space of real numbers to, or the set of real numbers to the space of n-dimensional vectors. So the next thing is that when we talk about this, well, because we're working in Rn, we can often describe the vectors not in terms of arrows, but instead in terms of coordinates. And if we do so, what we might do is we might represent it this way, where we'd say r of t is equal to, and then it'll have these coordinate functions. So I'll say f1 of t, comma, f2 of t, all the way up until, and if this is Rn, this would be fn of t. And that's how we'll often state a vector-valued function. So let's look at number 14 here, where I'm asking you to sketch some of the outputs to this function r of t here. I deliberately left some of the information off, so let's go ahead and restate this. This function r of t, it's a function r that maps from the reals to R2, and here we know, because I've used this bold line on this, that we're thinking about R2 not as a collection of points, but as a collection of vectors. And so let's go ahead and I ask you to find 3 of the vectors in this, and notice here my domain space. So what I could do is actually be a little bit more precise, because I've limited myself to the interval from 2 to 4. This would be the interval from 2 to 4 is getting mapped to the space of 2D real vectors. So let's just say that maybe this is a better way of describing that, because I've restricted myself to time values between 2 and 4. So what I'm asking you to do here is to go ahead and find 3 of the outputs from plugging in various inputs into this function. So let's go ahead and take r of 2. If we go to compute r of 2, this would be 2 times 2 minus 3 I hat plus 9 minus 2 squared, that's all in parentheses there, j hat. And so let's see here, that's 4 minus 1, so that's the vector I hat, and minus 9 minus 4 would be plus 5 j hat. And then we could go ahead and find r of 3. And I'm going to just show you show you various ways of representing this. So another way we could write one of these outputs as 2 times 3 minus 3 and 9 minus 3 squared. And so the output vector here would be this 2D vector. Let's see, 6 minus 3 is 3, and 9 minus 3 squared is 0. So that's another output vector. And then again, just showing you the various ways we could represent this. We could plug in 4. We could plug in any real number, because all I asked you to do was find 3 output vectors. So I could have plugged in any real number between 2 and 4, like 3.5, or maybe r of pi or something like that. But anyway, plugging in this fourth domain value, time equal to 4, would give us, in this case, we'd have 2 times 4 minus 3, comma, 9 minus 4 squared. And so the last output vector would be 8 minus 3 is 5, and 9 minus 16 is negative 7. And so I've got these 3 different output vectors. So what I could do is we could go ahead and give a sketch of these output vectors. And the way we choose to do this is we only look at the codomain space R2. So this is the x-axis and the y-axis, or the I and j axes, or whatever, however we're choosing to think about them. And I don't have time showing up here. And instead, we'll go ahead and label each one of these vectors by the time value of their input. So if I go ahead and plot this first vector, 1, 5, so let's see here, maybe here's 1, and up here is, maybe right here is 5. So this would be the position vector, 1, 5, and that's the vector I got when t was equal to 2. So I could label that as t equals 2, or I could also write, say, just r of 2 there. And if we go ahead and plot the second vector when time was 3, that's the vector 3, 0, so 2, 3, that's this vector right here. And so that happened, that would be the output of r of 3, or when t is 3, that would be r of 3, that output vector. And then the third vector is the vector 5, negative 7. So if I go out 2 more units, I'll jot those down, 4, 5, and then down 7, that'd be a little bit further down here, so that's negative 7. So that would be this output vector right here. And what I could do is I could do this many, many times, and I could come up with a sketch of this, this function in R2. What I'd like to do instead, though, is let's actually look at the graph in something called Calc Plot 3D, which I think I've shown you in class. But we're going to be using this more and more as we go along with this class. So let's go ahead and click that link and pull up Calc Plot 3D. So I've pulled up Calc Plot 3D, and this is a really versatile online program, grapher. And what I can do is I can ask it to graph a space curve. And then notice I'm going to graph this actually as a parametric function rather than a vector valued function, but of course the outputs are the same. So let's see here. Our first coordinate was 2t minus 3. So there's 2t minus 3, and I'm entering that. And then we'd have 9 minus t squared for the second. And then this is automatically going to do it for 3D. But what I can do is just say, let's just restrict ourselves to 2D. And then I think I need to still just put something in here for that to work. And now it's gone ahead and actually graphed this. Now we can't see this very well, so I'm going to go ahead and click on my axes panel. And then I'm going to adjust this to be from x equals minus 10 to x equals, I think 5 or 6 should be enough. And let's do y from minus 10 to 5. I think that's enough to see this. Yep. So here's the graph of this vector valued function, which is just a parabola. And maybe you anticipated that. And let me make this go out a little. That's kind of bothering me. Let's make this go out to y equals 10 as well. There. Okay. And so there's the graph of this vector valued function, restricted to 2D. I click that to restrict us to 2D. But let's actually see if we can see the vectors that are being created here. Because here, what we have is just the collection of points. And if you go look at what we were sketching, here I had the vectors that were the outputs, and the tips of these output vectors correspond to the points that form this graph here. But it's kind of hard to think about it that way without seeing the vectors. So what Calc Plot 3D is able to do, what we're able to do in it is, if you click this animate right here and you start dragging this along, we see that we see that something's happening. We've got some output vectors. Now the output vectors from the function that we sketched are here in blue. There are two other vectors being shown, one green and one black, and that actually leads to what we'll be studying later on in this course. Notice the black vector is always tangent to the curve. That's a derivative vector that we're going to look at. And then we've got a green acceleration vector here, and we'll explore that in a later class. So I'd like to actually turn those off. So let's see here. I'm going to click on the settings for this trace feature. That's this ship's wheel looking thing. And I can turn off both the velocity vector and the acceleration vector. I could actually turn off the trace. Well, we'll leave that trace point on because that's not really obstructing anything. And so here you can see the output vectors. And so, for example, we said, for instance, when t was equal to 2, that this was supposed to output the vector, I believe it was the vector 3, 5, and that's precisely what we see here. We also inputted the value of 3, and that gave us the vector 3, 0, and we also inputted the vector 4, and there's that one there. So you can see the vectors that we came up with by plugging in the various time values. And I just want to show you one more thing. It's not essential for this example, but I restricted the domain values to go from t equals 2 to t equals 4, and so I can go ahead and do that here so we can actually just look at the sketch of this function this way, and there is the sketch of that function. So there we have the graph of a vector value function in R2, and you can extend this. So we can turn off the restriction to R2, and we could look at this in R3. Let me just show you one more so you've got it. So let me put in sine of t and cosine. Let's do that the other way around. It doesn't really matter, but let's do the cosine of t, and let's do the sine of t, and let's do t. And I'm going to let t go from 0 to, let's go 6 pi. And here we've got, let's see here, I need to make this go up to 6 pi. Let's see here, 6 pi is about what? Be about, a little bit, about 20 or so. So here I've got the sketch of this function, and what we see is that the sketch of this vector valued function here is a helix in R3, and we'll be studying graphs like this as we go along, but you can see how that gets sketched. Now, if I look at just straight down the z-axis, which is kind of like looking at the xy trace, you see that the xy trace of this is a circle, which is what you would expect from the parameterization, just x of t equals cosine of t, y of t equals sine of t. So these are our vector valued functions, and we're going to spend chapter 14 studying them.